Hey everybody, here's some more Algebra 1B. We're talking about properties of exponents still. Exponents are the powers that we bring these numbers to. In our last video, we did this property where x to the a times x to the b becomes x to the a plus b. And this property where x to the a divided by x to the b becomes x to the a minus b. And we talked about why that is, like if you have x to the third times x to the fourth, there's 3x's multiplying and 4x's multiplying, which means altogether you have 7x's, so it's x to the 7th. The powers added, 3 plus 4, got a 7. And with division, if I have like x to the 5th over x to the 3rd, that's 5x's on top and 3 on the bottom. And these divide to 1 and divide to 1 and divide to 1, and you're left with 2x's. So we literally had 5x's and took away 3 to have 2 left. We're going to review that some more, get a bit more complicated with our expressions. We'll talk about the property for x to the 0, and in this video we will also do some scientific notation. When we do scientific notation, which is something like this, like 3.4 times 10 to the 12th, because it has these exponents that have to get dealt with. So scientific notation has to involve properties of exponents at some level. Let's just simplify real quick. 2 to the 3rd times 2 to the 7th. Those powers add to become 2 to the 10th. And 2 to the 10th is, I'm going to do this in my head, but out loud. 2 to the 1st is 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 1024. 2 to the 10th is 1024. X to the 5th times x is the same as x to the 5th times x to the 1st. And x to the 5th times x to the 1st is just x to the 6th. This one I wrote out, and then I apparently also solved it. X to the 8th divided by x to the 2nd is x to the 6th. Remember, if you have only numbers, your result will be a number. If you have numbers and variables, or numbers and letters, your result will have numbers and letters as well. Okay. So remember what I said last class, which was, when in doubt, expand it out. That property, that idea can still apply as we get more complicated and as we move forward. So now we have variables being multiplied with coefficients. You can think of this as 6 times 5x's as well as 2 times 3x's. And there's this property in math called the commutative property of multiplication that says I can multiply in whatever order I want. So it's really 6 times 2 times 1, 2, 3, 4, 5, 6, 7, 8 x's. This is 12x to the 8th. When you're multiplying, multiply the coefficients like you would typically, then add up the powers of the common bases. So 6 times 2 is 12, x to the 5th times x to the 3rd becomes x to the 8th. So here, 2 times 3 is 6. A squared times a to the 1st becomes a to the 3rd because there were 2 a's and we're adding one more a to it. B to the 1st times b to the 4th becomes b to the 5th. So this simplifies to 6 a to the 3rd, b to the 5th. Multiply the coefficients, add up the powers of the common bases. Division is the same. It's a bit trickier sometimes because there's fractions involved. And, that's just another layer to think about here. But I can split this up into 2 separate fractions. 16 over 10 times x to the 8th over x to the 4th. 16 over 10 is a fraction that reduces. Don't subtract. Don't do 16 minus 10 to get 6. Reduce the fraction to get 8 over 5. X to the 8th over x to the 4th, well, that is where the powers do subtract, right? There's 8 x's on top. There's 4 on the bottom. Divide to 1, divide to 1, divide to 1, divide to 1. We're left with 4 x's on top. So you can write this as 8 over 5 times x to the 4th, or you can write it as 8x to the 4th over 5. The same thing, they're both fine. With this next example, I'm going to make 4 fractions. Let's see. 25 over 15 is a fraction. X cubed over x squared is a fraction. Y to the 4th over y to the 1st is a fraction. And then we just have this plain old z out here by itself, so I'll call it z over 1. Just so I can think of this as being a fraction. If you wanted to, you could actually think of it as there's no z's on the bottom, so it's z to the 0. But that's silly. Let's just think of it as z over 1. Okay, let's start reducing fractions. 25 over 15 becomes 5 over 3. There's 3 x's on top and 2 x's on the bottom, so you subtract to have 1x. There's 4 y's on top and 1 y on the bottom, so you subtract to have 3 y's. And there's still the 1z. 1z. So if you want to write it like this, or like this, either of those two are acceptable. Okay, so this isn't anything new from yesterday, just more. You're best to think of these as separate fractions or as separate multiplications, and you're combining the things that are similar. Combine coefficients, combine common bases. You've seen me expand out several times on these problems. It helps understand things and helps explain things. So if you're in doubt, expand it out. Okay, what happens here? I'm going to simplify x to the 5th divided by x to the 5th. Notice something. By the properties of exponents, these powers would subtract, so I get x to the 0. But also notice that x to the 5th divided by x to the 5th is something divided by itself, right? If you have something divided by itself, you're always going to get 1. So x to the 5th divided by x to the 5th equals 1. But x to the 5th divided by x to the 5th also equals x to the 0. That means that x to the 0 equals 1. It's a property we're going to add. It's a new property. Anything to the 0 power is 1. Like 3 to the 3rd divided by 3 to the 3rd is 3 to the 0, but it's also something divided by itself. It's actually 27 divided by 27, which is 1. So 3 to the 0 is 1. X to the a minus a becomes x to the 0, which is 1. So there's our property. Anything to the 0 power is 1. Super convenient, super helpful. It's not 0. Don't think 3 to the 0 is 0. It's not. Finally, let's play with some scientific notation. Now, scientific notation is a way to express very large numbers or very small numbers simply. It's also a way to compare large numbers or small numbers simply. Basically, instead of writing out a whole bunch of zeros or a whole bunch of digits, we just keep track of how many zeros and digits there are. So this is 2.3 times 10 to the 8th. That means literally 2.3 times a 1 with 8 zeros. That's actually what that means, 2.3 times 10 to the 8th. But scientific notation lets us express a very large number in a small fashion. 2.3 times 10 to the 8th would just be a 2 and 3 with 7 zeros. So it's 230 million. Here's the hundreds, here's the thousands, here's the millions. 230 million. The way you convert from scientific notation to standard form, okay, is through moving the decimal point around. So this one right here is in scientific notation. This one is standard form, where you just have the numbers written out. What I'm going to do is I recognize this times 10 to the 8th means I take this decimal point and move it 8 times to the right. 1, 2, 3, 4, 5, 6, 7, 8. In the process, that gave me 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. Why 7 zeros? Because the first decimal movement didn't generate a 0, right? It was every movement after that. So there's one movement, but no 0. But then here's the next jump. 3, 4, 5, 6, 7, 8. Every jump that doesn't have a number after it creates a 0. So there's a 0 here inside that little loop, and a 0 here. And every single one of these jumps creates a 0 with a decimal now at the end. That's why there's 7 zeros, even though it was times 10 to the 8th. If your number is getting bigger, move the decimal to the right. But this is going to make our number smaller. Now, we haven't talked about negative powers yet with our properties of exponents. We will, probably in our next video. But if the power is negative, move the decimal to the left instead of the right. So this decimal is going to move left 5 times. 1, 2, 3, 4, 5. So the decimal is now right here. There's 1, 2, 3, 4 zeros. 0.1, 2, 3, 4 zeros, and 3, 4, 2. Very, very small number. So this moves the decimal 3 to the left. 1, 2, 3. So there's a 0 in this little slot and a 0 in this slot, and the decimal is now here. 0.00147. I usually put the 0 in front. You don't need to, but I like having it there. 0.000342. Okay, other direction. This is in standard form. Let's put it in scientific notation. Well, right now, to be in scientific notation, the decimal has to be directly after the first non-zero digit. Okay, you have to have a digit that isn't 0, and the decimal comes after it. So currently the decimal is right here. If the decimal is not shown, it's at the end. To move it from here to here, I have to go 1, 2, 3, 4, 5, 6. This would be 2.348 times 10 to the 6, because it took 6 steps. Right now the decimal is here. I want it here. That's 1, 2, 3, 4 movements. So 1.57 times 10 to the negative 4. Why negative 4? Because this is a small number, not a big number. Big numbers are positive, small numbers are negative. This one here has 3, 6, 9, 12, 15 steps. Each of those steps is a group of 3, so it's 6.4 times 10 to the 15. All right, lastly, these numbers down here are almost in scientific notation. But the decimal's in the wrong spot. Right now it's here, but it's supposed to be here. This is, I think, the trickiest part of this lesson. I'm going to move this decimal 1 to the left. That made this number smaller. 2.3 or 23.1 got smaller. 23.1 became 2.31. Since this got smaller, this has to get bigger to make up for it. So this is going to become 2.31 times 10 to the 10th. And here, this will get smaller, so the power has to get bigger to make up for it. So it still stays in balance, so we're not changing the value at all. If both the number and the power got smaller, we'd be changing the actual value of the whole number. We don't want to change its value, so one shrinks and one increases. This decimal needs to be here, 1, 2. I'm making this number bigger, right? I made this number bigger from 0.015 to 1.5. Since I made that number bigger, I have to make the power smaller. And negative 7 is actually less than negative 5. It's kind of weird. I have to make it less. Negative 7 is less than negative 5, so I made it smaller. This is going to get bigger. So this is going to get smaller. We'll talk about that more in class. That's a tough idea there at the end. But other than that, I think we're doing good. See you next time.